Um, yeah, again, my name is Mike, and I'll be discussing random wire antennas, which I titled end-fed antennas here. Same thing. I think they're generally called random wire, but there's a little more thought that goes into it than pure randomness. And on the title screen here, I've been a lifelong fan of cartoons and comics and that sort of thing. And Phil Gildersleeves is far and away my favorite ham radio cartoonist. So I poked around looking for something end-fed related that he drew. This was the closest I could get. So I thought it'd be a fitting way to start things off. Now, a quick aside, when I go into slideshow mode, I tested this earlier. For some reason, it doesn't move forward. So I'm going to keep it in the mode it is now, which unfortunately has all those icons up top. But yeah, before getting into the talk, I thought it would be helpful to give a very brief bio of myself, a few bullets here, just so you understand my perspective, where the talk is coming from, my strengths and weaknesses, those sorts of things. And I became a ham a little late in the game compared to most. It wasn't until age 40. I had been a shortwave listener as a kid and a teen. I'd occasionally heard hams, but somehow it never really sparked the interest that the shortwave stations did. And then in my in my late 30s, I became more and more interested and finally started reading Now You're Talking and was licensed back in 2003. And you can see from the state silhouette in the upper right that I was born, raised, and lived most of my life in the tiny state of Delaware. And it was only really just before becoming a ham that we hopped across the state line into Pennsylvania. So still not very far from the old home state. And that actually ties into the talk shortly in a small way. So now professionally, I work as an electronics engineer for the Army, and I'm in a communications electronic warfare group, comms EW, as opposed to radar EW. So from that, you can guess that I'm more of a signals guy. I am not an antenna designer. My background in antennas is typical of other hams, maybe even less than the antenna enthusiasts. So I wanted to put that out there so everyone understands that, I'm learning my way here as well. One of the things that, again, this leads into my interest in the end-fed antennas, is when I'm at work, 40 hours a week and then some often, is 100% digital modes. And so I have absolutely no problem with digital modes. But when I come home just to shift gears, to change it up, I tend to go analog, mostly CW, a bit of sideband, bit of local repeaters, but by and large, CW operator. And my wife wonders how I can work on radios all day and then come home and play on radios, and I think this has a lot to do with it, going from digital to analog. Of course, I also tell her the Army doesn't know that I love what I do. I do it for nothing, but don't tell them that. And so now all of these things together kind of pointed toward my interest in learning a bit more about the end-fed antennas. Because one thing I noted is if I drive just 10 minutes down the road to Delaware and I bring along my favorite QRP rig, a little Elecraft K1 I built, I'm not even sure when, maybe 10 years ago or so. I really enjoy using that rig. And if I operate in Delaware and people hear the QTH from Delaware, I get a string of QSOs almost without fail. If I do the same in Pennsylvania, not so much. So it's a little bit selfish on my part. I drive a few minutes and I'm guaranteed to get more QSOs in the log. Or maybe it's generous. I'm giving out a tough to reach state. All of your point of view, I suppose. But when you are operating portable or travel for work or even vacation, when my wife, a little apprehensively puts up with my bringing along the QRP rig, she's actually very good natured about it. She knows I enjoy the hobby and I try to strike a good balance there. But again, when you are portable, the name of the game is to get set up and on the air, be able to break down quickly when you're done. And end feds just can't be beat for that. So at the last bullet, I'm here tonight after Dan dropped me an email and said a web page that I put up about end fed antennas caught someone's eye and they thought this might be an interesting talk. Now, there's not great technical depth, but I think there is a lot of useful utility in this. So I hope between the two, it'll be an interesting talk. And I find it interesting that with ham radio and even other hobbies like genealogy or similar things that I spend my time in, I enjoy sharing the work I've done. I think it's, the excitement, like all of us getting together here tonight, which, by the way, I think this is a fantastic idea, these 2-week talks. I was unaware of these. Reminds me of grad school, the monthly or weekly symposiums. And anyways, so to share the work, I would put this stuff up, different things I work on my University of Delaware webpage, which I luckily still have back from when I was a student there years and years ago. I can't believe the webpage has not gone away. And what I noticed in the weblogs is that this page on random wire antennas is just amazingly popular. I didn't expect it at all. There are certain things that I put out there that I think, just the coolest things and people will love it. And, and it seems I'm the only one that feels that way. This, on the other hand, seems to have struck a chord. The only other page that is maybe even a little more popular is one devoted to GNU Radio, which some of you might be familiar with, the software portion of software-defined radios. And a lot of the tutorials there are either very, very basic or very advanced. And I tried to write a few that are kind of middle of the road, and that also seems to have struck a chord. But in any case, back to tonight's talk. Here's a brief overview. So after, these first few intro slides, you can see in the lower right, out of the slide count, that I've only got another dozen slides. So it's I think, a fairly concise talk. Room for chatting afterward, we'll see. But the first bullet is a theme that kind of runs through the rest of the slides, that these end feds or random wire antennas are both easy and challenging. The easy is almost self-explanatory because as far as antenna systems go, nothing's much more straightforward than hooking one end to your rig and throwing the other end in a tree or somehow getting it up high. Challenging is what I mentioned earlier. It's not truly random wire. If you make a random cut, you might or might not be able to work the bands you want to work on that piece of wire. So a little bit of thought has to go into it. I want to start with a little bit of history as well. I always find it interesting in radio in general and ham radio in particular to look at the history because it's a relatively new field. And in this case, a lot of the work went back to the first years of ham radio. And after that, I'll go through a little bit of theory. And a little bit, not because I'm shying away from it, but because that's really all there is with this topic. And we'll talk more about that. And then that'll lead into the calculation and the ultimately the computer program that I've got on the web page that brought me here tonight. So with that, we'll jump into the talk. I should quickly say, I do not expect anyone to read this. This is a snippet of the QST article. But when I was trying to dig into the history a bit of these end-fed antennas, going back as far as I was able in the QST archive, which is really worth your time on some rainy afternoon. It's fun digging through those. As much fun for the ads as anything else. So I found this antenna. The first sentence, a question, which is maybe unreadable, but how long should a 40-meter antenna be? And what I find interesting in the snippet I put up here is the table in the lower left, that Mr. Lang, back in 1926, started experimenting. He put to bear what theory he was aware of, but keeping in mind just how new the field of radio was. And a lot of that would be in the academic journals, not easily accessible to the typical ham. Certainly harder than today when there's no internet, no Google. You know, how can we get by without that anymore? So in the left column, he has a list of wire length, tip to tip, where he experimented with the different lengths. And most interesting to me is the right column is the shape of the antenna. I think it's pretty safe to assume there was no clear awareness of far field radiation patterns or other subtleties, at least in that day, of making best use of an antenna. So he tried different shapes in addition to the different lengths. And the article discusses that in more depth. But what I find interesting here is just the initial effort at a combination of experimentation and a little bit of theory in there. So the bottom bullet on this slide, I found a web page by Ward Silver, where he was curious where this ever famous equation 468 over F came from. So he went through a lot of ARRL publications, not just QSTs. And the earliest reference he could find was in the 1929 handbook, with no discussion where this number 468 came from. And that's what we'll focus on the theory slide coming up in a little. And the fact that there's no discussion makes me suspect that it's probably got a little more age to it than that whoever came up with it would probably, like me being excited sharing things on the web, be excited to share it in an article or in some manner. But in any case, while this no longer is pure experimentation, we've got an equation. That 468, it's a bit of a black box that bundles up a lot of complicated aspects of an antenna system. And some of the biggies I put here, which we're all very much aware of, but for emphasis, height, ground conductivity, am I by the ocean? Am I in the desert somewhere? Of course, wire thickness affects the manner that the electrons flow. And of course, nearby conductors. If I'm in my favorite park in Delaware, trying to make some contacts, and then a big metal box truck pulls up in the parking lot 30 feet away, it will affect how the antenna works. Maybe better if I'm lucky, more likely than not, worse. But, so we're evolving from the initial experimentation to we have an equation here. And then 10 years later, from 1926 to 1936, this is the first article, at least that I'm aware of, that explicitly addresses end-fed antennas. So the author, Yardley Beers, is writing about his friend, Mr. Siegel, W3 EDP, who at the time was a new ham, apparently with boundless energy, and he experimented making antenna after antenna, trying different lengths, pure experimentation, despite the fact that 468 over F was in a handbook in 1929. Mr. Siegel, maybe he thought the antenna was so different that didn't apply. Who knows? He, as a new ham, he might have not been aware. We don't know, but this article discusses his I think, nearly 2 years of experiments. And for 40 meters, he hit upon 84 feet being the magic length for him, for his environment, depending on what he had nearby, how high did he get it, all those things mentioned earlier. And then he started looking at counterpoise, which, essentially it's easier to feed a dipole from the center. So counterpoise is a little bit like throwing another end of the dipole on the ground. And because of the changes in environment and the other characteristics mentioned, the length is affected. So he found that a counterpoise of 17 feet created just the right antenna for him. So lower on this slide, the third bullet, you can see basically what that article boiled down to, that Siegel used over 1,000 feet of copper wire to come up with those numbers. And I just can't imagine how many antennas and how many times he, a short one works well, longer works better. I'll make it really long. Now works worse. And, that's sort of just pure experimentation, which is why I wanted to put these first two bullets up. That as scientists, for sure, also engineers, the goal is first principles design. We have the speed of light, we have Boltzmann constant, all of these basic properties of the universe we live in, little Lego building blocks. And wouldn't it be nice to snap them together, make little subsystems and bigger, and then finally the ideal antenna system that works perfectly in my environment? But we all know that's not practical, probably not possible. There are just so many things. Your environment now is different than your environment in 12 hours or 12 days, 12 months. That things change, let alone movement in the environment, which again adds to that change. So we can't really do that. But we generally don't have the time and energy that W3 EDP had to get a big spool of wire and start trying things. So his method, and what we as hams very often make use of in a decent amount, is empirical. We try something else, see what works best, what works worst, and based on that, we start to develop a theory. And so true learning, true development in a field is this back and forth between empirical and ultimately first principles design. And at the bottom of the page here, 468 over F, that's a little closer. It's probably maybe not the best we could do, but it's not so bad. And especially for hams, we're okay with adjusting the antenna. It's not like it's on a satellite in space where if it's wrong, we're not going to shoot up there and change it around. So here's the slide on a little bit of theory. So if we start with the good old C equal F lambda, speed of light is equal to the frequency of the signal multiplied by the wavelength of the signal. And then just rewrite it in this first bullet to lambda equals C over F, replacing the speed of light C with, decent approximation, 300 million meters per second. And we'll divide that by a frequency also in millions of hertz so that the millions or megas cancel, giving us a nice length in meters. But we also know from basic antenna theory that a half wavelength antenna is, it's enough. And when we're operating portable or in a temporary setup, usually we want to do the least we can to get the job done. So instead of a full wave, we'll divide by 2, and we've got our half wavelength in meters is equal to now 150 over the frequency. So at this point, come to think of it, my bullets are probably a little out of order, but for anyone who's had any electromagnetic field theory, you remember a dipole, and if you haven't, don't worry. The dipole you have a point charge in space, some charge plus q, and you have another charge a distance away that's minus q. So that's a dipole. You know, your two opposite polarity points. Uh, Clearly, we can't make use of that. So the next step is to connect them by a wire. And you know, the full name of the antenna is a trapped dipole antenna. Harder to say though. So now we've got this dipole trapped in our wire, each end of it. But of course, we still got to get that wire to the rig. So we need the feed line. So all of these things go from the perfect world of a dipole, not the dipole antenna, but the dipole, to a less than ideal antenna. And we have the fact that we're not dealing with infinitesimally sized objects. Now we've got end effects in the wire. So the bullet under the boxed equation shows that these end effects typically will increase inductance and reduce capacitance, which has the ultimate effect of making your physical antenna appear, electrically speaking, appear longer. And essentially, you know, what's also going on is that you're not moving quite at the speed of light in the copper. So when you bundle all of these things up, 0.95, that's kind of our empirically derived number. That's our black box. Might be right for some environments. I don't think it's common that a ham cuts an antenna to 468 over F and says, this was perfect. Usually we grumble because we have to trim it back. I don't think I've ever used that and had to add to it, but in any case, oh, and I forgot to say here that when we convert from metric to standard units for all of us here in the US, that third bullet becomes the fourth. That's where we finally reduce that to 468 over F. And as I pointed out before, and again on this slide, you know, it's a mix of empirical and first principles. You know, we do our best, C equal F lambda, and then we take into account the fact that there is just too much going on for us to wrap our arms around all of it. So 0.95 is good enough for an initial stab at it. Now, when I tested this earlier, the animation was a little choppy, but you can see at the bottom, I took this from Wikipedia. It's a really nice animation. So here we have a center-fed dipole, our rig down there at R. And what I really like about this animation, though, is we've got the electric field, we've got the RF signal in green washing over the copper dipole, and it's inducing a current back and forth, back and forth. And what's nice to see is that 0 voltage line cutting right through the center of the dipole. So nice and easy to match. And yeah, normally that's what we want. But again, working portable, now we have to get the feed point erected as well as the ends of the two legs. And I admit to being a little lazy when I'm out in the field, and I like to do less than that. So what's really important to see here is notice where the peaks and valleys are. They're at the ends of the dipole. So that high voltage is the hardest point when we have the best signal, a resonant signal. We have the highest magnitude voltage, and it's the hardest to match from the end, which is unfortunate because what that means is we're going to adjust the length of this antenna so that we don't have to deal with those really high voltages. And in different words, what that's saying is give me a weaker signal just so that my impedance matching network, my antenna tuner, can deal with the voltages. And it's symmetric antennas, as we know, transmit, receive. So the problems, there are both directions. Now freezing that, in this picture here, we have half wavelength of the voltage signal. And again, that's frozen at the point where we've got the maximum voltage magnitude at each end of the antenna, the hardest to match. Oh, I almost forgot the point of this slide, the title. So imagine that this is cut for 80 meters. Now imagine that you want to operate 10 meters on this very same dipole. Instead of having half a period of that sinusoid, you're going to have 8 times as many, you're going to have the multiples on there. So those high voltage points are going to occur at half wavelength multiples. And coupled with the fact that we want to use this on multiple bands, now we've got lots of places where there are high voltage, and we want to avoid all of those points on the antenna. So this is repeating to some effect what I just said, that we want the general use antenna. And on the third bullet, I do in parentheses say, unless you're using an end-fed half-wave, because imagine you have a single band QRP rig. In that case, your best signal is going to be when you've got that highest voltage at the end. So you really want to invest in a nice, beefy impedance matching network. So that way you can draw out the weakest signals and just make the most of that. But for multi-band antenna, like my little Elecraft K1 is on, it's a 4-band rig. So an end-fed half wave on one area is not going to solve the problem for the other bands. I didn't word this too well on the second to last bullet, but essentially saying multiples of half wavelengths, you've got the same danger zone, so to speak. So moving into the calculations, one way, and I say it's truly effective, is a slide rule. It's actually easier than a calculator. So you can pull it out from the back of your drawer. And I hope this is coming across, but on the zoomed in portion of the slide rule, the hairline on the D scale is set to 468, and across from it on the C scale is 7 megahertz. And moving over to the index on the C scale, underneath of that, I know it's hard to see on this slide, but somewhere around 66.5 feet would be the half lambda, the half wavelength length for your antenna. But keeping in mind, we do have potentially multiple bands. In addition, we have multiples of these half lambdas on a given band. The higher frequencies on an antenna that's also cut for lower frequencies. So you've got a handful of calculations, absolutely can be done, but computers make it easy, let us be a little lazy, and it's kind of fun to write the code if you happen to be a programmer. So this is an example, top to bottom, stepping through the calculations for 4 bands. And it's no coincidence, these happen to be the very 4 bands that my K1 rig uses. But the software, you can pick and choose the bands you want, and it'll quickly adjust for that. So on the top one, we're taking a look only at 40 meters. And if you remember back to Mr. Siegel, W3 EDP came up with 84 feet as a good length for an end-fed antenna on 40 meters. We can see it falls nicely in the white zone here, the lower voltage areas. I should also mention on all the graphs, the red rectangle at the very left, that's for quarter wavelength and less. We don't want to go less than that, because then we're making major compromises, especially on the transmit. Excuse me. So again, back to the top one, what we see on the slide rule, we just calculated somewhere around 66.5 feet, which you can see a little pink rectangle at that point, and then multiples of that at the far end of the dipole, of the end fed. So for one band, we want to avoid those when we've got our typical modest capability impedance matching network found in, I was going to say QRP rigs, but honestly, a lot of tuners, even in a base station. On the other hand, if this is your only band, I do recommend, as I mentioned, using an end-fed half wave, and you want to hit those, in this case, pink colors. Colors, incidentally, have no meaning. They're just to distinguish the different bands as this exercise moves forward. So then the next row, for 20 meters, you can see we have everything from 40 meters. What you can't easily distinguish is that the bands from 40 meters are widened a little bit because of just where the bands fall. It's not exact overlaps from lower end to upper end. And then we have this other area from around 100 feet for 20 meters itself. Then when we drop down to the third graph, we have all of those, and then we have even a few more and the sets of multiples for 15 meters, and then yet again for 10 meters. So you can imagine, and I think I still have it up on the web page. For fun, I did one with all the hand bands, and I think there are actually no lengths that are usable on all the bands when you're using an end fed. Because now that's, again, assuming a modest antenna tuner. So now maybe I should have shown this slide before those rectangles, come to think of it. But this, excuse me, should have brought a glass of water here with me. These are the calculations that you would perform on the slide rule. So in bold italics, 7 to, well, roughly 7.1 megahertz, 14 to 14.2, and so on. You can see as you go higher in frequency, you've of course got more multiples on this wire that's cut long enough for the lowest frequency. So each of those, I guess that's somewhere around 20 maybe calculations. On the slide rule, you could sit there and come up with 20, and that's where I say I think that's actually faster than a calculator, unless you write a little mini program on your calculator. In any case, these are the exact calculations that the computer runs through, which is what makes it easy for you to pick and choose the bands you care about. Maybe this trip, you only want to work 15 meters because there's a contest. Calculate that. Next time you want to be able to work all the bands. Whatever. The software does make it easy. And in closing, last slide here, the picture is just a repeat of that fourth one a couple slides back, all in red, a little easier on the eyes than the many colors. And it's excuse me, I guess I'm not used to talking so long. We've got many lengths we can choose from, and you don't want to go too short, because keep in mind that you can match it, but imagine that sine wave where what we're doing is we're cutting back and we're saying, I'll take even less amplitude on that sinusoid. So it's going to take an even stronger signal to get through. So you don't want to waste your time going too long, but you don't want to sell your rig short by going too short and only being able to have QSOs with the guys with S6 signals. So little bit of trade-off, like everything. And I've got the URL here. So this is where the web page is. And if you bump up one, just chop off the word random wire. I've got a handful of other ham things. Honestly, nothing earth-shattering, just reflecting my interests. But on the random wire page, the NFED page, is the source code to generate this in both C and MATLAB, those two languages. MATLAB is actually very expensive, but there's a program called Octave, which is more or less drop-in replacement. And with that, that basically brings the talk to a close. Thanks very much for your attention. I'll do my best to answer any questions there might be, but we'll caveat it by again saying I'm not an antenna guy. So thanks very much, everyone.
Well, for not being an antenna guy, I thought you did a pretty good job with the presentation.
Thank you.
If you don't mind, lower your screen, your desktop.
Yes, I will be glad to.
Okay. And are there any questions out here? I don't see hands raised. What do you got there in the chat there, Barry?
Nothing.
Nothing at all, huh?
Either covered in depth or
yeah, I think
well known.
Wait a minute.
Dan has his hand raised.
He does. Dan, would you take it away?
Mike, I got to compliment you. You're the first person I've encountered in amateur radio that called CW analog.
Oh,
everybody else thinks it. I mean, it is in fact closer to digital in the world of ones and zeros than most of the multi-tone encoding we do is all digital. So I salute you, sir, for being a purist.
Well, thank you. Yeah, I could see the argument from both sides, definitely.
Okay, anybody else? Can't let Mike Dan take it all. Well, okay. This is going to be a shorter than normal.